All right, so vector operations is the next installment in the series of doing vectors, and basically the operations you think addition, subtraction, multiplication. Yes, we are dealing with those. The first one we're going to talk about is scalar multiplication, where scalar is a number, and in this case, it's going to be real numbers only that we're dealing with. Uh, and you are doing exactly what it says. You are multiplying your vector by a particular number. So when you look at this, you see that we have vector v equals k times u. As you know, this is means to be vector, but we do write vectors using arrow notation. But we have vector v equals k times vector u, where the vector is the absolute value of k times as long as vector u. So k is basically representing the scalar, and you are multiplying each vector by a particular real number. So in this case, we're looking at vector u as our starting vector. So then vector v would be 1/2 vector u. In other words, it's going to be half the length, half the magnitude of vector u, as you can clearly see here by this picture. Let's look at this one. It says 2 times vector u. Clearly, this one is twice as long, as you can noticeably see, as vector u. This one is negative u. Negative does not tell you the length. It basically tells you the direction. As you can see, it's going in the opposite direction of vector u, which was talked about in the last installment of vectors, the very first one. But if you take the absolute value of k, which would be 1, as you see, it does not change its length. And then this one here, negative 3/2 vector u, basically means that we change direction, and we are 1.5 times as long as vector u. But that's basically vector operation. Now, the next little bit that you're going to see is going to be dealing with the picture, the pictorially of vector operations. You do need to know how to draw these different types of vector operations, not just be able to calculate them mathematically. Okay. So for two vectors, there are such things as parallel vectors, as you guys can see. But basically, for two vectors to be parallel, one is a scalar multiple of the other. So you have this theorem here that basically says that if vector v and vector u are parallel, then you know that vector v equals k times vector u. In other words, it's a scalar multiple, okay? And vice versa, if vector v equals k times vector u, then you know that v and u are parallel. So basically, if you're given two vectors, one is vector v and one is vector u, and you can noticeably see that vector u is twice as long as vector v, then you're going to know that they're parallel because one is a scalar multiple of the other. And it also applies with not just pictorially, but also applies with component form. Remember, component form is used when you have a vector that's not in standard position. So if you have a vector that's u1, u2, and then you have the scalar multiplication going on, then you're basically multiplying each component in that component form by that particular scalar. Okay. Now, vector addition, we're going to talk about next, and then vector subtraction. We're going to look at them pictorially, and then we'll actually do some problems mathematically. But there are two ways of looking at adding vectors. There's the triangular method and the parallelogram method. So basically, I'm describing the situation that occurs when you're dealing with triangular method. And before you go forward, I actually want you to pause the video, and I want you to see if you can actually draw what I am describing here. Okay, so you have two vectors, vector u and vector v. I want you to draw a vector so that the component point of vector u and the initial point of vector v coincide. Okay, the vector joining the initial point of u to the terminal point of vector v is the sum, also known as the resultant, of vectors u and vector v, and it's denoted by the notation of vector u plus vector v. Can you draw it? So what I want you to do right now is I want you to pause this video, and I actually want you guys to try to draw it on your paper, okay? And then when you're ready to see it, then press play. So please pause the video and try to draw what I've described here. Hopefully you got something like this. To go back over that paragraph, it says draw a vector so the terminal point of u and the initial point of v coincide. This is here, right? This is it right here. So using that terminology from the last video that says the terminal point, which is basically the end of the vector, and the initial point, which is the beginning, coincide means they go together, they touch each other. And then it says the vector joining the initial point of u, here's the initial point of u, and the terminal point of v, right there, is the resultant. Okay, the resultant is this, u plus v. Okay, this is the triangular method. As you see, it makes a triangle. Okay, the resultant vector, the sum, basically going from the initial point of one vector to the terminal point of the other vector. Okay, that's known as the triangular method. Now this next method, which is your parallelogram method, I want you to do the same thing. I want you to pause the video and try to draw what I'm describing. Okay, so again, you have two vectors, vector u and vector v. It says draw the vectors such that the initial point of u and the initial point of v coincide. Now hopefully you understand what coincide means now if you didn't know before. The vector joining the common initial point of u and vector u and vector v to the opposite corner of the parallelogram formed by the vectors and as its adjacent sides is the sum, aka the resultant, of vectors u and vector v, and is denoted by, again, u plus v, vector u plus vector v. Can you draw it? So I do want you to take a moment. I do want you to pause the video, and I actually want you guys to try and draw it. Okay? Please do this. Pause the video. Hopefully you got something like this. Again, it says draw a vector, so draw your two vectors so that the initial points coincide. There they are right there. And then it says the vector joining the common initial point, which is here, okay, with the two have in common, and then the opposite corner of the parallelogram is the resultant, okay? As you can see, here's the parallelogram. Here's the side that's parallel with vector u. Here's the side that's parallel with vector v to form that parallelogram, and then there's the sum, there's the resultant. Now, the parallelogram method could basically be used when you have both vectors in a standard position, which basically means they're both located at the origin. So you can find the resultant by basically adding the two, by drawing the resultant from the common initial point to the opposite of their parallelogram. Now, a combination of the parallelogram rule and the triangular rule deal with vector subtraction. So it says to draw the vectors, vector u and vector v in the usual way. The usual way meaning the parallelogram method, being that it deals with standard position. Then we draw negative vector v starting from the terminal point of u, and we add u plus negative of v to get the difference of vector u minus vector v. Now the difference of the two vectors, u and vector v, is the diagonal of the parallelogram with this initial point, the terminal of v, and its terminal point, the terminal point of u. Okay? So here's what that looks like, okay? Here's the usual way, vector u and vector v using that parallelogram method. And so to continue to create the parallelogram, we still have our vector u here, but this time our vector v is heading in the negative direction, as you can see. It says we draw negative vector v starting from the terminal point of u, going down so it hits the other terminal point of vector u. Okay, there you go. And so then to connect the initial point of vector v and the terminal point of vector u, technically we would have been adding these two, so it would have been u plus negative vector v, but a positive and a negative make a negative, and so that's why it turns into subtraction there. Okay, now if you're like, what just happened, don't worry. Once you actually get to the examples, it's going to make a little bit more sense of when to use the parallelogram method versus the triangular method. And also when we revisited the question, when we revisit the question from the midterm, you'll notice how you're able to do that. So we're actually going to look at some examples now of applying addition and subtraction, okay? So we are going to consider the vectors, vector u at 2, -3, and vector w at 1, 3. And I do believe that probably should have said, yeah, no, that's right. All right, so now it says write down the components of vector v equals 2u. Remember, 2u basically means scalar multiplication. So we're actually going to take vector u, and we're going to multiply it by 2. Okay? So to do that, we are just going to multiply the scalar by each component. So vector v is going to equal 4, -6. And there it is. Simple enough. And remember, when we have to write vectors ourselves, we use arrow notation. We cannot denote that bold-face notation. All right? Now it says find the symbol u and the symbol v and compare them. Now remember, these symbols here mean magnitude. So we're actually going to find the magnitude of vector u, and we're going to find the magnitude of vector v, and we're going to compare them. This is basically just getting the practice using scalar multiplication right here. So as we know, since they're already in component form, we can use the Pythagorean theorem type method, which is basically u1 squared plus u2 squared. So that's nothing but 4 plus 9, which is the square root of 13. And then we'll do the same thing with vector v. That's going to be 4 squared plus a -6 squared. That's going to give us a square root of 52. Now, yes, you do want to use your knowledge of simplifying radicals. This is basically 4 times 13. And so when you take the square root of that, that gives you 2 square root of 13. So there are your two magnitudes, magnitude of vector u and the magnitude of vector b. Now, we have to compare them. Well, if you notice, vector b is nothing but 2 times vector u, okay? So the magnitude of vector b equals 2 times vector u. Please apologize, my pen was connecting together, okay? And so basically, we know that the two vectors are indeed parallel because one is a scalar multiple of the other. I mean, that's what we did have to do to find vector b anyway. Now, this next one, we're going to draw vectors u, vector b, 2 times vector w, vector u plus vector w, and all these other ones. And then we're going to comment on our results from part C. Okay, so all this basically goes together. So we're going to use the fact from the previous slide that we have u and w and v, and we're going to draw each one of these vectors, okay? So what you see here is my makeshift coordinate plane, okay? So I'm going to go ahead and label my axes. Okay, you should do the same. There's I have 1, 2, 3, 4, 5, 6, 7, 8. Okay. So now we're going to draw each of these, okay? So I'm going to go ahead, so I don't have to keep flipping back and forth. I'm going to write down what each one of my vectors were. Vector u was negative 2, 3. Vector b I found to be 4, negative 6. And vector w I found to be 1, 3. Okay? And actually what I'm going to do is I'm going to use different colors so you guys can actually see this a little bit better. So vector u will be in purple. Vector b will be in red. Vector w is going to be in orange. And so that way, when we're doing like the resultants and things like that, you'll be able to see the different colors. So 2, negative 3. 2, negative 3. So I went 2, negative 3. And since it is component form, that means I'm going to be in standard position. So I'm starting at 0, 0, and I'm going to 2, negative 3. And I want to make sure I include the arrow because I do need to indicate direction. So there's vector u. Now vector b is at 4, negative 6. So 1, 2, 3, 4. 1, 2, 3, 4. Negative 6. Okay. Remember, they were parallels. Just one was a scalar multiple of the other. So of course it's going to lie in the same direction as vector u. And lastly, vector w. Again, we're going from standard. We're in standard position. So 1, 3. We're going from 0, 0 to 1, 3, making sure we indicate direction, and there's vector w. Hopefully, that actually wasn't too hard, okay? Now we're going to do 2 times w. 2 times w basically means that it's going to be twice as long as w heading in the same direction. So 2 times vector w, what is that? Hopefully you thought to yourself that, oh yeah, I know what that is. That's going to be 2, 6. So all I have to do is multiply vector w by 2, okay? And the reason why I'm doing the dotted lines along the vector that they're parallel to is just so that I don't lose the color, okay? But if you had to draw this yourself, you would not do that. So on the IB exam, do not do the dotted line through the vector that is like kind of coinciding with. Just draw right over it, okay? Now the next one we're going to do is u plus w. I'm going to do that in black, okay? So vector u plus vector w. Now, when you are doing adding, okay, you can think, all right, well, since vector u and vector v, their initial points are coinciding, I can use the parallelogram method to draw this, okay? So basically, our initial point for our resultant for u plus w is actually going to be located right there, 0, 0. And it's going to basically be the diagonal that forms between vector u and vector w, okay? Algebraically, to figure that out, then you do exactly what you think. You add vector u and you add vector w. What's 1 plus 2? Well, that's 3. What's negative 3 plus 3? That's 0. So you already know that your terminal point is going to be at 3, 0, and there you go. That's vector u plus vector w. Now real quick, just for the sake of the method, if I were to continue, if I wanted to show you the parallelogram method, well, I would need to draw another vector w, which has a slope of 3, 1, right? Like there would be the vector w there, and then over here I would have to draw vector u going opposite direction, so that would be down 3 over 2. And of course, my picture is not, oops, I'm sorry, wait. So that would be up 3 over 1, so I actually put it here, and then down 3 over 2, actually put it here. And as you see, it's at the it's hitting the opposite side of that parallelogram. If you can't see it too well, I do apologize. It's not perfect to scale. If I had an actual regular coordinate plane, then you guys will be able to see a little bit better to scale. Okay. The next one we're going to look at, not to make this too bad or too confusing, let's look at, I'll do this in brown, vector u minus vector w. Okay, clearly if we subtract, that's going to be a 1 and then a negative 6. Okay, so let's see, 1, negative 6. Right. Sorry guys, hold on. I'm confusing myself now. So u minus w is basically that we need to go from vector u and then a negative vector w, okay? So I am going to actually have to draw that back in. So I'm going to draw back in that neon green parallelogram here, okay? Of course, my pen is sticking, so it's not helping my situation here. So like I said, it's a little makeshift one, but kind of bear with me. So then this would be your negative vector w, right? That would be your negative vector w, and this would be your vector u that continues in the same direction, okay? So then to draw u minus w, we would need to go from the initial point of vector u to the terminal point of negative vector w. So this right here, the brown would be vector u minus vector w. And if you notice, okay, I go over 1 unit and down 6 units to actually get to my my terminal point. Okay, that's how you would draw that. Okay, so using the combination between the parallelogram method and the triangular method that I was describing before. Okay. Now, what I want you guys to do is I actually want you guys to do u plus w, u minus 2w. Once you do these two, and then this last one, b minus 2w, okay? I actually want you guys to give that a try, okay? Press pause, draw it out, and then when you're ready to see the answer, press play. So pause the video. Here is the pretty looking version of everything, okay? Proper scales and everything like that, okay? So you were to do b plus 2w, so that meant that you need to go from the okay, when you actually added b plus 2w, you would have gotten 6, 0. So of course you're using the parallelogram method, going from the initial point to the opposite corner of that parallelogram. As you see, the dotted red line, the dotted pink line to form that parallelogram. You also had to draw b minus 2w using that same type of parallelogram, going opposite from the terminal point of vector b to the from the initial point of vector b to the terminal point of negative vector negative 2w. That's what you see in the black dotted. Okay. And then the last one you had to draw was, I forgot this that quick, u minus 2w. Okay, so here's u, 2w, and then Again, the likelihood that you have to do all 6, 7 of these in one on the IB exam, probably not likely, but to be able to draw maybe 1 or 2 of them, yes, that's more likely. Now, vectors can also be represented in unit vector form. Unit vector form is using i's and j's, where I and j are vectors with a length of 1 unit in the directions of x and y respectively. Vector I and vector j are called base vectors. Okay, and so unit vector form, like I said, uses i's and j's, and it's just another way to represent a vector. Okay, vectors can also be represented in that column format, where the value that goes with vector I is at the top, the value that goes with vector j is at the bottom, and of course that basically represents direction. So the top number deals with your x's, the bottom number deals with your y's. So say if you're talking transformations, okay, 3 vector I plus 4 vector j means a movement of 3 units in the positive x direction, and then 4 units in the positive y direction. So that might look familiar from your midterm again when it asks you to find the value of, I think it was t and q. Well, t would technically represent your x direction, either moving to the left or moving to the right, and then q would represent moving up or moving down. I think those were the values of the variables. I might be backwards, but the top component deals with x and y, x's, bottom component deals with y's. Now there is such a thing as a 3-dimensional vector. You know, we're looking at the x, y, and z axis. Will you have to draw that? Definitely not. Will you have to do some type of operation with it? Most definitely. Okay, so you do need to realize that if you ever see three variables, you are dealing in a 3-dimensional one. Same as before, you have, say for example, you have 3, -2, 1. That means you are dealing with a vector. Dealing with a vector in a 3-dimensional plane. 3 represents moving in the along the x direction, the -2 y direction, and then 1 in the z direction. And of course, then you'll have 3 vector I minus 2 vector j plus vector k there. All the operations are the same with unit vectors as well. So that's addition, subtraction, scalar multiplication, etc., etc. Now in this example, it says find the terminal point of vector b equals 3i minus 2j if the initial point is -2, 1. Okay. So whenever you see unit vector form, do not let that throw you off. If you need to put it into regular component form, do so. That's 3, -2. If you want to use column format, you can do that too. Don't let that notation throw you off. Okay. But basically, we know what vector b is. We know what the initial point is. The only thing is we don't know the terminal point. So if you think back to the formula that I gave you a really long, not a really long time ago, but at the very beginning of the very first vector video, it said that u2 minus u1, and then u2 minus v1. I think I might be off on the notation, but this is what you use to go to component form, right? I might be a little bit off, but you basically subtract to get to the actual vector itself. Okay? Well, the fact is you already know what the vector is, and you know what the initial point is, but you don't know what the terminal point is. So then you can use that as basically a formula. What you see here. Okay? You know that some number minus -2 should get you 3. And you know that some number minus 1 should get you a -2. That's how you actually get the vector that you want. So basically, this is nothing but a simple linear equation. You subtract 2. Over here, you add 1. So then you know that your terminal point is 1, -1. Doing a little bit of math. A little bit of simple math with that. This one says find the initial point of vector b if the terminal point is 5, 0. I want you guys to do this one on your own. When you're ready to see the answer, press play. You're looking for the initial point when you're given the terminal point. Hopefully you got this as your initial point. Take a look at the math. Then when you're ready, continue on. I want you guys to try this one on your own as well. Pause the video. Do this one on your own. Hope you guys got this as your answer, -5, -5. Okay? Once you guys get a little bit of practice using the unit vector form and the operations, so go. This one's very simple. Go ahead and pause this video. When you're ready to see the answers, press play. Hopefully you got these as the answers. Pause the video, double check if you need to. Okay? Because the next part, continuing on, actually now I want you to find these respective ones. Okay? Remember the absolute value bars mean magnitude, so you're going to do a little bit of Pythagorean theorem here. Okay, use your values from before to try to help you answer these. Press play when you're ready to see the answer. Hopefully you got these values as when you did them. So you had to actually take your resultant that you got when you did vector u plus vector v from the previous one to find that it was 2 root 2. Same thing with vector u minus vector v to get 4 root 2. For the next one, you actually had to do them separately. You had to find the magnitude of u, magnitude of v, add them together. And remember, when you're adding radicals, they do have to be alike. That's why you get 2 root 10. And then also when subtracting them, they have to be alike. And there is such a thing as a zero vector. There is such a thing as a zero vector. Okay? I am going to go ahead and skip this one. But it pretty much works the same way. Actually, if you can go ahead and work out this problem, that would be great. So pause the video and press play when you're ready to continue. This one, we have 2 vectors. It says find the vector x such that x fits this type of situation right here. Okay? Now the one thing is, basically, everything will kind of just treat this like, regular variables and things like that. You sure can, right? You can go ahead and bring your x vector over to the same side. And I really hate this pen because it's sticking together. Bring your u vectors over to the same side. So you'll have 2 vector u plus 3 vector v equals 8 vector x. Okay? And so then to actually find vector x, you would have this type of equation right here. So basically you treat them as variables, but just for right now, because then what you can actually do is you can actually do 2 times u. So 2 times u would give you 2, 10. 3 times v would actually give you 9, negative 12. So when you actually add them together, you'll have 11, negative 2 divided by 8. So then your x vector would be the result when you actually divide those by 8. Okay, so you can do a lot of things with vectors, like normal type of operation. All right, last example we're going to go through is actually kind of similar to the one from your midterm. It says vector u and vector v form 2 sides of a parallelogram. We have to express each of the following vectors in terms of vector u and vector v, which means that we have to represent each one of these vectors in those terms, okay? So we're told that from the vector ps and the vector pq are vectors v and vector u. So to actually find vector pr, if you look at it, pr looks like it's using the parallelogram method for vector u and vector v. So we can actually represent that as vector u plus vector v. And that's how we can represent vector pr in terms of u and v. Now for pm, where m is the midpoint of rs, we can use the fact that, hey, well, this still again uses the whole parallelogram method, except this time we're looking at possibly not the full vector u, but maybe only half of it. Check it out, right? Does that make sense? Because if m is the midpoint of rs, the midpoint is going to be half of vector u, right? This is half of vector u. So then it's still dealing with the parallelogram method, so it's just nothing but what half of u this way is a negative vector b. So again, we can use the resultant and say this is u minus vector b. Oh, I'm sorry, I have them backwards. I didn't pay attention to them. Sorry. This actually goes with b. This one goes with u. So it should be b minus vector u. And then the last one of qn. Where's q? Where's n? Okay, I see it. Okay. Q to n. Okay. Well, it looks like we're kind of stopping halfway in between something when you agree. Okay? And it's almost as if we know that this is b, this is negative u, so it looks like it's half the resultant of b minus u. We could also write as 1/2 b minus 1/2 u. Okay? So do you see how the parallelogram and the triangular method work when it comes to the drawings as well as working out the operations mathematically? If you have any questions, by all means, you can send them to me. Go ahead and start on your prep work and just bring any questions that you guys have to our next class.